Hello everyone, welcome to the third week interaction session for the course on advanced robotics. So my name is Soumya and I am Prime Minister Research Fellow at IIT Gandhinagar. So this is the third week of the session and till now we went through some practice problems. Then we also saw what are DH parameters apart from origin of robotics and everything. We saw what are DH parameters and how they help in getting the forward kinematics of a robot. So we went through these and today we'll be mostly focusing on forward and inverse kinematics for the system. So there will be various practice questions in which we'll be seeing the forward and inverse kinematics. But before that, since all of these are still based on DH parameters only, so I would just take you through what we had studied in the last class so that it becomes easier to uh, remember the things. So DH parameter is a systematic way to define the geometry of robotic manipulators, and it really establishes a relationship between the links and joints using four values A, alpha, D and theta. We already saw. So why it is used? Because it simplifies forward and inverse kinematics, because it has a systematic way of doing things and we stick to that. We stick to the type of axis that we are supposed to choose. The x-axis should be along the link, then z-axis should always be along the axis of the joint in case of revolute joint, or along the axis in the case of prismatic joint. So all of those. And we also saw various advantages. So the important thing that I want, yeah. So we learned that A is the link length, alpha is the link twist, and then theta is link angle, and D is the offset. So we worked for two DOF manipulator. So this is the example, just I would reiterate. So here in this case we had A, alpha, D and theta, where A was the distance uh, A was the distance between the yeah, A was the distance between the z-axis. Z is the angle between alpha is the angle between the z-axis. X is the distance between the two x-axis, and then we have the angle which is theta. So here are four parameters A, alpha, D and theta. All right. So these are the parameters that we were supposed to find for each joint, and then we had uh, found out the transformation matrix for each joint, multiplied them to get the overall homogeneous transformation matrix. So that is all we had done. Another thing is the convention. We usually took z-axis to be out of the plane and x-axis to be along the link lengths. So there were a couple of rules also that we had followed. For example, let x-axis be along the uh, joint axis, and then if the x-axis were intersecting, then we cannot have the x-axis along the perpendicular, the shortest distance between the z-axis. We cannot have x along that. So instead, in that case we took x to be perpendicular to the plane containing the z-axis. So these were the rules that we had followed, and yeah, so this was the general way in which we substitute the value of theta, alpha, everything, and we get the answer. So instead of doing it again and again, we have a general thing also. So this was important thing. A is the link length, link twist, link offset, and joint angle. All right. Now, yeah. So this was for our robot and all. So let's move today to our topic. Okay. So the very first question that we have is just based on, I hope it is visible. I'll just increase the size. it's better. Yeah. So there is a Puma robot, and how many links are there in Puma robot? How many axes we have to assign? I mean, Puma robot has been discussed,
Six.
right? Six, and the last three axes coincide. Okay. So the question asks you that a Puma robot is shown below in which the frames have already been assigned. So what is the first row of the DH table? That is only the question. So the first link that we have is a revolute joint. So let's answer for that. Let's say we define the axis. We define Z0 to be going out of the plane parallel to this thing. So Z0 is here. Okay. X is lying somewhere in this plane, and Y can be taken as the dot product of, I mean, X cross Y should give you Z. So in that way, Y can be chosen. Now, if we are supposed to find the DH parameter for the first joint, okay, so this is your joint, this is A alpha D theta, this is distance along Z, angle Z axis, distance x, angle along x axis, angle between x axis. Now, for joint 1, that means everything we have to find out has to be between 0 and 1. So what is the distance between Z axis? There is no distance as both the lines are intersecting. So it is 0. What is the angle between Z axis? It is also 0. What is the distance between x axis? So you can see that both the x1 and x0 are intersecting. Hence the distance is also 0. And the last one is, what is the angle between x-axis? So what is the angle between x-axis? So since this is a revolute joint, that means the angle, it can move by some angle, right? So x0 is already in the global frame. X1 can move. It can always move because it can rotate. So if it can rotate, we can say that it moves by an angle of theta 1. All right. Similarly, you can write for 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. I encourage you to write all of them, but the question right now asks only for one, so I'll be answering you, but do practice for all of them. Okay. I hope this question is clear. It is just the same question from the last class. Nothing new with this. Okay. So let's move to the next question. Okay. Before we move to this question, I understand that you have already learned what is forward kinematics and what is inverse kinematics. Last class also we had discussion regarding the same, but I want to ask what is known and what is unknown. What I mean is what is already given and what we are supposed to find. And I want this for uh, forward kinematics and inverse kinematics. So you can answer in the chat box, or you can also turn on your mic and speak. I encourage you to turn on your mic because the screen that is being recorded is only for the screen that you are also being presented. So anything you write in chat is not recorded. So if you speak, that would be good because we'll have it recorded. So yeah. So what is known in case of forward kinematics?
Theta 1, theta 2, etc. are known, and the unknown parameters are x, y,
Right,
z.
right. So theta 1, theta 2, etc. Whatever is your joint variable, it is known, and x, y, z is the thing that you are supposed to find, which is end effector position. I hope everybody is clear with what is end effector. That should not be a problem. End effector is basically the last manipulation point of the robot, which is supposed to interact and manipulate the environment. All right. Now, for inverse kinematics, it is just the opposite. You are given x, y, and z position. That means you already have end effector position with you. All right. And then you're supposed to find, okay, what will be theta 1, what will be theta 2, what will be d in case of prismatic joint. Okay. So you are supposed to find out what are the joint variables. This is the difference between forward and inverse kinematics. Now, forward kinematics is really simple because you have one value of theta 1, one value of theta 2, and then you find what is the end effector position. But in case of inverse kinematics, it becomes difficult. Why it becomes difficult? Let's say this is the center point, and then let's say we want to be here. So this is the end effector point that you have already, let's consider it to be planar. Okay. So you have been given xy, that this is the point I want to reach. Now, the solution is not unique. You can reach this point. You can have link like this. And you can also reach in this way. So there can be multiple solutions to the same thing. So this is the reason why inverse kinematics does not have a particular solution. So you have to solve it in two ways. So one is that you can go with a geometric method, where you can try to find out, okay, what is the geometry, and then you reach there. The other is that you use algebraic method, where you find, okay, what is my cosine angle and how I should reach there by squaring the terms or doing all those things. So there are two methods possible. Both of them are widely used. So yeah, we'll see in the questions also later. Okay. So the question asked here is, forward kinematics is defined as forward kinematics is defined as given the joint angles. Joint angles are given to me and the link parameters are given to me. What I am supposed to find out? I am not supposed to find out orientation position of the base frame. I'm not supposed to find out the position of the last frame only. None of the above is wrong, because I want to find out how does my end effector position and orientation look like. So this is the correct option, because we are interested in what is the XYZ position of the end effector and how it is oriented with respect to the base frame. So these are the information that we want to extract. That is why we want to find out, yeah, for everything for the end effector. Any question?
Ma'am, ma'am, is it same as the position and orientation of the last frame?
Um, it may be true, it may not be true, because I mean, last frame can just have a distance. So I'll show you why I'm saying this. So let's say I have this robot, and yeah, so okay, so I consider it to be my end effector position. Okay, and if I have something attached to it, and this is not a joint, this is not revolute joint, this is not prismatic joint, it is just joint from here. So what can be the thing that, okay, just a second. Okay, so this is your last frame, right? Everything XYZ you are finding with respect to frame, and this frame is same frame. The frame is not changing. It is just that you have a link and you have just made it as a tool. So this end effector position remains here only, and this is what we are interested in, because this would move as the end effector moves. So everything is here. So I think if it is last frame, if it I think if it would have been written that position orientation of the last frame, it should have been the same. Yeah,
Okay, ma'am.
because end effector is the ultimate thing we are looking at, and even if you consider that frame to be the last frame, it is good. If you consider this frame to be the last frame, it would just be separated by a link and you don't have a joint here. So both of them can be correct. Yeah. Okay. Now, in the 6DOF Puma robot that we have already seen in question 1, the last three axes intersect for the following reasons. So, this part was discussed in the lecture because you have all the three axes. So, I showed you in the figure. So, these three, here there are three axes and all of them coincide, and that is really the reason why we are able to find out the inverse kinematic solution. So it has a long proof and everything has been covered in the lecture, so I'll not be delving deep into that, but yeah, this is the reason. This is important. Okay. Okay.
Ma'am, that is orthogonal too, right? All are at 90 degree.
What?
Uh, Last axis x, those are orthogonal also, intersecting last three axes.
Three axes are orthogonal. What do you mean by that?
Ma'am, my question is that whether the last three axes are they are intersecting at a point.
Uh-huh.
What will be that angle, ma'am? That last three axis angles?
So it is your wish, na, how you wish to take. I mean, you have all the three things here only, at this point only. So whatever is the, for example, if the rotation is along this, you take z axis to be along this. Here you can take it to be along this. For the last piece, you can take it to be along any other direction. So let's say there are three axes, all of them are intersecting. They need not be along the same lines, but yeah, since they all of them lie at the same place, we don't have a link length in between them, so we are not going to separate them and all of them are together. That is the only reason.
Okay, ma'am. Fine.
Okay. Inverse kinematics is defined as given the position and orientation of the end effector, find what. So as discussed now, we find joint angles and joint lengths, because yeah, for all. We don't find the joint positions because there is no meaning with this. Joint rates can be associated with a velocity, but we'll see in the next class that we have Jacobian for this. And we don't find the position and orientation of the remaining frames. It is rather we find what are the angles that we are getting from them. So yeah, fourth one. Okay, this is a question that we have already solved. I think this is very easy, but still, uh, this question was already discussed. I hope it is already clear with you. If not, you can tell me, I'll solve it for you. I mean, what should I do? Is it required or not? Or wait, I'll explain only. It won't take much time. Okay, this is L1 cos theta 1. This is L1 sin theta 1, right? Now, so if you measure it with this is theta 1. So this complete angle is theta 1 plus theta 2. This complete angle is theta 1 plus theta 2. Okay. So what is it? This is L2 cos of theta 1 plus theta 2. This is L2 sin of theta 1 plus theta 2. So when you write x, you will write it L1 cos theta 1 plus L2 cos theta 1 plus theta 2. y is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. All right. So the first one is only the correct option. This we had already discussed. It is simple geometry. Okay. Okay. So this is again a theoretical question. What is a dexterous workspace? And if you remember this, then you should also remember what is a reachable workspace. So how do we differentiate between dexterous workspace and reachable workspace? It has something to do with orientation. So definitely this is the wrong answer.
Dexterous workspace in all orientations.
Okay. And reachable in?
Reachable is the like boundary at the end limit. It can reach at the end limit only.
Then it is possible with one orientation only. So let's say we have a 2R manipulator. Okay. And something of this type. But what I would really want with this is to reach this point. We have it somewhat this, not this type. It would reach somewhat more. So if it is supposed to reach this point, it would have to stretch itself completely. The angles cannot be less than 180 degree. So you'll have to reach here, and the way in which it is possible is just one orientation. Whereas if you're supposed to reach this point, you can do it in many ways. You can do it like this and like this. You can go like this, like this. You can go like this and then like this, maintaining the same uh, link length. So there are a number of ways it is possible. So it is possible in all orientations. That is called dexterous workspace. Workspace means where the end effector can reach. What is the region in which you can manipulate the things? Okay, and this is associated with in one orientation. Okay, so your answer is in all orientations. Okay, this is a question that we'll solve now. So I request all of you to solve. There are two ways in which we can solve. One is algebraic, one is geometric. So we already saw the geometric one you already saw a geometric way of solving this in your lecture. I'll be taking you through the algebraic one. So yeah, let's start. So this is a 2R planar robot. What is a 2R planar robot? It has two revolute joint, and then it is able to move in the plane only. That means if my robot is like this, so I have a revolute joint here, I have a revolute joint here, and it is able to move in this plane only, this plane. Okay. So for a two dots, 2R plane robot given in question 5. Is there any figure? Yeah, this is your figure. Uh, the position of the end effector is given by this. So your end effector position is given to you. (1.83, 0.75). Okay, if end effector position is given and you want to find out theta 2, what is my theta 2? That means what are we doing? We are doing inverse kinematics. So we already had the questions for forward kinematics last time. We'll see inverse kinematics now. Okay. So we want to find out what is theta 2. So we have this end effector position already given. So let's say xy is 1.83 comma 0.75. It is already given to you. L1 is equal to L2 is equal to 1. Okay. Now from using these relations, we'll be using these relations, all right, to solve the question. So what we can write, L1 cos theta 1 plus L2 cos theta 1 plus theta 2 is equal to x, right? Put L1 and L2 to be 1. Then you'll write cos theta 1 plus cos theta 1 plus theta 2 is equal to 1.83, right? Yeah. You'll have this. Now from the second equation, so let it be your first equation. Okay. Let's move to the second equation. L1 sine theta 1 plus L2 sine theta 2, sorry, sine theta 1 plus theta 2 is equal to y. All right. So sine theta, please solve along with me. Sine theta 1 plus sine theta 1 plus theta 2 is equal to 0.75. This is your second equation. Let's square and add both of these equations. Okay. So what we'll get? We will get L1 cos cos square theta 1 plus sine square theta 1. It would be 1 plus cos square theta 1 plus theta 2 plus sine square theta 1 plus theta 2. That means it is again 1 plus 2 cos theta 1 cos theta 1 plus theta 2 plus 2 sine theta 1 sine theta 1 plus theta 2 is equal to 1.83 square plus 0.75 square. Okay. So from here we can write 2 plus how we can write this 2 cos theta 1. Okay, let me take 2 out from here and then we'll see. So what can be the thing that is written here? Let's consider these. I'm sorry. Okay, let's consider this term and let's consider this term. What would we get when we solve this identity? Cos theta 1 plus theta 2, sin theta 1 plus theta 2. So you can see it will be cos A cos B plus sin A sin B, right? It is this identity only. So what is cos A cos B plus sin A sin B? Is this cos A minus B?
Cos A minus B.
Right, very good. So this is cos A minus B. So cos theta 1 minus theta 1 plus theta 2. Okay, this is your term which is equal to 1.83 square plus 0.75 square. Can anyone solve this and tell me what is the value?
$3.91.
Okay, 3.91. This is correct. So from here we can write uh, this. So from here we can write 3.91 minus 2 by 2, and here it would just be cos theta 2, because we will get cos minus theta 2, cos minus theta is equal to cos theta. So cos theta 2 is equal to this value. Okay, do not find the value of theta 2 from here, just find out what is cos theta 2. So your cos theta 2 you'll get to be equal to nearly 0.9557. All right. Once you have cos theta 2, don't take theta 2 is equal to cos inverse. Don't do that, because we might have multiple solutions and then we won't be able to find them. And the other thing is, you might have seen in the lecture as well, it was well explained that we might get the values of theta 1 and theta 2 in such a way that the links are not connected. You'll have the values, but the links are not connected, and yeah, numerically you get the answers, but those answers won't make sense. So do not find the value of theta 2 from here. Let's find sine theta 2. Then we'll go for tan theta 2, and from there we'll try to get. Okay. So this is 1 minus cos square theta 2. So can you tell what is the value for sine theta 2?
Zero point 0.308.
Okay. Did you? Okay, okay. I think you did not take to 4 places, right? This one, this value? Or did you?
No, ma'am.
Okay, okay.
We have to take 4 places. Okay.
I mean, for accuracy, it is good. Else, we lose on values. So, the number of places you take, that it is that good.
Ma'am, when we are taking 4 positions, we'll get 0.2965.
Okay. Yeah. So, after this, you can write theta 2 is equal to tan inverse of sine theta 2. Yeah. Sine theta 2 or cos theta 2. So from here you can find theta to be equal to 0.2943. So I'll tell you the command also. So in MATLAB what we write is a tan 2. It takes a tan inverse and it considers both sine and cos to be positive. Everything is from the first quadrant. Okay. A tan 2 sine theta 2 cos theta 2. This is the way we can write in MATLAB. So okay, you have obtained theta to be from this value. Let's convert it into degrees. So 0.29. Is this correct? This tan value is correct? Can you verify once? Tan inverse of 0.2965.
Ma'am, I'm getting it as 17.24.
Okay. Okay. So you are trying to find out in degrees only, right? Yeah. Yeah. Degree. It's not converted into radian, but this gives you answer in radian. Then we have to multiply it into 180 by pi. Okay. So you will get it closer to 18 degrees. I think that is the nearest option we have. Yeah. That's correct. So 18 degrees. So your theta 2 is 18 degrees. All right. If you want to find out theta 1 also, we'll have to use the geometric constraint. The question does not ask, hence I'm not telling you that. But the thing is that you'll have to like uh, find out what is this theta 1 angle. So your theta 1 angle would be something like this, and then you have the other theta 2 angle, and then you'll have to find this angle. Then by geometric manipulations you'll be able to find theta 1 also. So that is the way it would go. Okay, let's move to the next question. So for the 2-DOF planar robot arm given in question 5, the same question to our manipulator 1, how many inverse kinematic solutions are possible with end effector in the center of workspace? So yeah, let's say this is my, if it is talking about center, I'll draw a circle. Let's say this is my center of just a second. I don't need to do this. We'll consider the same robot. Let's say we want to reach a particular point xy and it lies within the workspace. All right. So if we have to reach this point, how many configurations are possible? You have a robot, let's say I draw one configuration, L1, L2. There can be one more configuration, right? It would be in this way. This is L1, this is L2. There can be definitely multiple more. You should be sure about this, that it is not going to be this. It's not possible. Because if you are able to achieve with a combination of L1 and L2 by having some joint angle in between, stretching them would take you to somewhere else. It won't take you to XY, it would take you to the end of workspace, right? So this is definitely not a possible option. So what are the possible options for reaching the position XY in the workspace itself? There are two configurations only possible. So one is, so there are two elbow configurations basically. So both of these are, this is elbow down, this is elbow. These two configurations are possible for reaching this position. So you just have two inverse kinematic solutions. for reaching this end effector position. All right, you cannot have any more than this. Okay. Okay. For the manipulator given in question number 7 is the same to our manipulator. All right. End effector position remains the same. Link length is the same. We want to find out what is the value of theta 1. So we'll proceed with the next part. So from there we had already got that theta 2 was 18 degree, right? We had already got this. And apart from this, what we also know from the first equation, we had cos theta 1. So L1 and L2 were also there. Okay, I'll write it for the first time. Cos theta 1 plus theta 2 to be equal to 1.83. From here you can write cos theta 1 plus cos theta 1 plus 18 degree is equal to 1.83. From here you can write cos theta 1 plus, let's expand it. So it would be, what is cos A plus B? We did it just now, right? We'll write that only, cos A cos B minus sin A sin B. 0.951 into cos theta 1 minus, you'll get these values, 0.309 into sin theta 1. So these are the value of just cos 18 degree and sin 18 degree, all right, is equal to 1.83. Please solve with me. Okay. Yeah. So these are the values. So this is your first equation, let's say. Okay. Then what about the second equation? Sin theta 1 plus sin theta 1 plus 18 degrees is equal to 0.75. So your sin theta 1 plus 0.951 into sin theta 1 sin A cos B plus cos A sin B. This is what will be written here. 0.309 into cos theta 1 is equal to 0.75. From here we can write, you see there are two sin theta terms, so we'll add them. I think I did not do for this one. Okay. This is not your first equation. So here you can write 1.951 cos theta 1 minus 0.309 sin theta 1 is equal to 1.83, and this is your first equation. Okay. 1.951 sin theta 1 plus 0.309 cos theta 1 is equal to 0.75, right? Okay. Now these two equations, from these two equations we have to solve for theta 1. But it does not appear to be that simple. One thing we can do is, we can try to square and then we can proceed with an algebraic method. Another thing is, since we see that cos theta 1, sin theta 1, these things are only present. Okay, we have some value on the right side. Can we express it in matrix form? Matrix form will actually give us an easier way of calculation because we can take the inverse and we can manipulate it. So we just have to find cos theta 1 and sin theta 1. From any of them we'll be able to find theta 1. Okay. So I'll express it in matrix form. Other thing you can do is square and add. Okay. So from here we can write actually, I think you can do one more thing. You can, in the second equation, you can divide it with, no, you won't be able to. I thought we can divide it with cos theta 1, but that would also lead to getting you tan theta 1 and 1 by cos theta 1. So sec theta 1. So there will be again two values. No, that is not possible. We need these two equations. Okay. So from 1 and 2. How can we write it in matrix form? Okay, something has to come here and I'll tell you this is a 2 cross 2 matrix, alright. Here I am going to write cos theta 1, sin theta 1 and the values are 1.83 and 0.75. Can you tell me what we are going to have here in these places?
First row element 1.95 minus 0.309.
Okay.
Second row element 0.309
Hmm.
and 1.951.
Very good. So this is the value that we'll have. Once we have this, we can take inverse. So I will take inverse. I'll tell you. Let's consider it to be x is equal to b. A inverse A x is equal to A inverse B. This becomes identity matrix, right? This becomes identity matrix. So from here we can write x is equal to A inverse B. So you need to find the inverse of this matrix. It's a fairly simple problem. Can you tell me what is the inverse of this matrix? Once you have the inverse, multiply it with B matrix. So you'll get from here cos theta 1 sin theta 1 to be equal to some value. Can you find the inverse and multiply it with B? Can you tell me what are the two values that will get here? This and this. Got the answer?
Ma'am got A inverse.
Okay, just a second. Yeah, A inverse is
First row is 0.5
0.5.
and 0.0791.
Okay,
And second row is minus 0.0791 and 0.500.
okay. And when you multiply it with 1.83 and 0.75, what do you get?
Ma'am, 1 minute.
Yeah. I hope everyone is also solving. Please solve these, it would be very helpful for you.
Today, I'm going to try out the new generative fill tools in Photoshop.
Ma'am, the values are cos theta 1 equal to 0.9743
Okay.
and sin theta 1 equal to 0.2302.
Okay. This is really good. You have found out the right answers. Very good. So from here, theta 1 would be cos inverse of 0.9743. And this time they both, okay, both of them should lead you to the same result. So that is a basic sanity check. So from here you will get it to be 13 degree. If you try to find out theta 1 is equal to sine inverse approximately 13, you might get it something 12 point something. Okay, theta 1 is sine inverse of 9743. From here also, sorry, 0.2302. From here also you will obtain it to be nearly 13 degree. So your correct option is,
Ma'am, is it okay to take cos inverse and sin inverse?
yeah, here it is okay. I mean, we have done all the calculations and then we are taking it here. So I'll tell you. Where we had that. Yeah. So here in this case, we did not take directly from here because we can get cos theta 2, cos minus theta 2. Both of them can lead you to the same value. That is why we calculated sine and took tan, so that we get everything. मतलब a tan 2 में taking the positives of both we get the angle. Whereas in this case, our situation is we get theta 1 to be cos inverse of something. Okay, cos theta 1 and sin theta 1 both are pointing to the same thing. So both of these have to be satisfied. So both of them, you can check that both of them should give you some positive value, and if both of them are equal, they are correct. Sin inverse and cos inverse should lead you to the same values. I mean, if they are in different quadrants, they could be a problem, but in this case, they are not. We can directly take the cos inverse and sin inverse. Okay, now, yeah, a tan 2, I already said that it takes the positive sine and positive cos values. This is the function in MATLAB. I think you should use this to uh, see what is the answer that you're getting and play with it. So, okay, I'll show you one thing. I came across it on LinkedIn today. I'll show you. I don't know if this link is going to open here. I'll show you it on your on my system. Okay, I think I'll be able to present now. Okay, I think you're able to see my screen now. Yeah, PowerPoint. Yeah, so this was something that I saw, and it is related to forward and inverse kinematics only. So it is like you want to apply this to your robot by fully deriving the equations. So yeah, there are two ways to approach this problem. As I said, the algebraic one and the geometric one. So this person actually used the geometric way, and then what he did basically is to identify triangles in the complete geometry of this robot. So he identified all the triangles that he could get and used trigonometry to solve for joint angle variables. So what are the angles? All of them are revolute joints only in this case, no prismatic joint. So this person tried to use the geometry to find out all the joint angles. So he came up with multiple possible solutions, and then you have certain constraints which have to be met to get the answer. So yeah, I'll show you. Yeah, you can see this robot. It has 4 revolute joints. So one is this joint, theta 1, theta 2 is along this, theta 3 is along this revolute joint, and then theta 4 is like this. And all of them are function of end effector position. What is the end effector position? Which is corresponding to x, y, z and r. R is what is the angle of rotation that it has achieved. Basically theta in our case. So you can see that he has made all the, he has taken the given configuration, he has taken the top view, the side view, and then from the top view he made the triangle. Okay, this appears to be in this, here is the revolute joint and here all the links are attached. Then he tried to form a triangle in a very similar way that you have learned. He has taken this theta 1, he has taken this angle to be rho, and this angle to be phi, and then all the link lengths as well, L2, D2, all of these. And then he tried to find out a relation. This is then this is the first triangle that he took. This is the second triangle that he took. So he is basically trying to solve this triangle only with multiple triangles. And then he took the side view and got the geometric relation, then the first triangle and all. And then he came up with this, that okay, the forward kinematic solution, we found out that r is equal to theta 2 plus theta 3 plus theta 4. So in our case also we had seen when we had 3 links and all of them were planar. let's say they were not moving in some other direction, all of them had revolute joint parallel, and the robot was completely planar. Then we saw that the complete rotation at the end we get is sum of all the three rotations, theta 1 plus theta 2 plus theta 3. In this case it is not theta 1. I think you should check why it is not theta 1, probably due to the axis being aligned in a different way. So this way he was able to find this, and then he had the final equations coming out like this. The theta 1 is tan inverse of this quantity for righty configuration, for lefty configuration, elbow up, elbow down. So these are things you can do. So I'll share this link with you also. This is already in the slide, but still I want you to see this post. And this person writes in the comments that he is trying to get all of these things documented. So it would be a good material for you. I'll paste the link in the chat box. Okay, please see this. It is good for you. And yeah, one more thing I wanted to show.
Photoshop to go from this to this. Obviously, I need to get rid of my hand.
Animation is what got a lot of us
Yeah. Are you able to hear the video?
3D artists in the 3D world. Today we'll discuss one of the main topics surrounding
Is the sound clear?
No, ma'am.
Oh, you're not able to hear it.
The sound is not clear.
Okay, sound is not clear, but you're getting some voice. Okay, I'll see.
3D world. Today we'll discuss one of the main topics surrounding 3D animation, which is the difference between inverse kinematics, known as IK, and forwards kinematics, known as FK, their pros and cons, and when you should use one over the other. Keep in mind this video is more of a general overview, and there is no objectively right or wrong answer. Each animator will have their own workflow. Let's start with forwards kinematics since it's easier to understand. FK works with parenting. If you rotate bone 1, all of its children will go with it. If you rotate bone 2, all of its children will move, but bone 1 will not, because it comes earlier in the chain. This is the default behavior of any armature you try to animate, and by default all of your movements happens in arcs. IK on the other hand works by using control bones. You won't need to rotate each joint anymore, just by moving one control bone. The rest of the chain will adapt to it. This will usually give you a more natural movement, and the movement happens in a linear fashion. IK can also be
So we read this about forward and inverse, right? That if there is end effector position, whatever angle is required, that we should get once we are trying to move the end effector. So this explains you that for forward kinematics, it is like if one of them is also moving, you will be able to reach to some different configuration of the end effector.
used to quote-unquote stick joints to a place. More on that later on. Whether you want a linear movement or an arc movement by default depends on what you're trying to animate. Say you want to animate a walk cycle. Generally speaking, you'll want the arms to move in an arch fashion, since that's how we naturally move our arms when walking. In that case, you'll use FK on the arms to have that natural arch from the get-go. In the same walking cycle example, you may want to keep the legs in IK. That's because when you're walking, you lift your foot up and your knee automatically bends. Doing that with FK takes a bit longer because you'll need to manually rotate the leg, then the knee, and the foot joint while trying to keep a linear movement. Generally speaking, it's easier to use IK in this scenario. If your leg IK control bone controls the whole leg, you are able to move the torso without moving the legs. That's great because it sticks the legs to the ground, making animations like jumping easier to deal with. If the legs are set to FK, when you move your torso down, the legs will go under the ground, since they are parented to the torso bone. One example is when you want a character to push something. If you keep the arms in IK mode, put the hands on the object and move the torso. You'll see the hands will not move, but the arms will to adapt to that change. The same logic goes for the legs, and anything else you may have in IK on, like tails. Our character from Character Z have an IK, FK, switch for you to use. You can find our characters and plenty of other or FK, go for it. I'll link down below some must-watch videos by Survey.
This person has said, how do you animate the characters using inverse and forward kinematics? What is the thing? What is the joint angle do you give to achieve a particular position? Or do you take it to a particular position and see if the angles that you're getting are feasible or not? So that is the way it is used here. So yeah. And you saw that LinkedIn post, right? So there also how we are doing everything is really important. I think I'll share this link with you also. So with this, we'll end today's class. And one more thing is that in the next class, we are going to see Jacobians. So has anyone gone through the lectures for Jacobians? I mean, till now we are, yeah,
No, ma'am.
okay. So till now we are just talking about the positional relation. What is the end effector position, what is the joint angle? So all of them are either theta or x and y. What if we want to find a relation between velocity? What if we want to find out how does end effector velocity relate to the joint angle velocity, or joint velocity that we say, the rate of change of angle? So if you want to find such relations, Jacobians come into play. All right, so we'll have multiple questions from there. So I request everyone to go through the lectures for Jacobians, and redundancy is also there. So please have a thorough understanding of both of those lectures. And yeah, we'll meet next Monday. Thank you.
Thank you, ma'am.
Thank you, ma'am.